Calculus Study Guide. Think of it as a manual for clickable calculus of a single variable. It was originally written as an ebook separate from Maple itself. But since the release of Maple 2021, it has been incorporated into the help system. So every recent copy of Maple contains the complete guide. Immediately, the question comes up, well, what about somebody with an earlier copy of Maple who might want access to the guide? And I have been instructed to say those people should contact customer support or sales to discuss the options for obtaining the ebook. Used to be you would go to the Maple bookstore online and order it through that medium. It's very inexpensive. Often it was bundled with a copy of Maple. Since they put it into the help system, alternate distribution methods have to be employed. So, customer support or sales. Now, what is this guide? It's a supplement to any standard calculus book. It's not designed as a replacement for the calculus book. It's a supplement. It demonstrates how Maple augments a calculus course and implements the syntax-free approach to using Maple that MapleSoft calls Clickable Calculus. So it illuminates calculus and it illustrates how this enhanced learning is implemented in Maple without a need for first mastering syntax. So in this webinar, we're going to show how to access the guide in the help system, and we'll sample enough of it so that you can judge whether or not it's a worthwhile addition to your slate of tools in the classroom. Well, what are some of the features of this guide? As we said, it's not a replacement for calculus text. We assume that the user has a calculus text at hand. But it provides insights that a paper text maybe can't. And it's a very good manual for implementing the syntax-free use of Maple in single variable calculus. There are 69 sections. Calculus books are pretty thick, about 1,000 pages in a calculus text. They weigh 5 or 6 pounds, 69 sections. There are more than 460 worked examples. And we'll take a look at a few examples to see how they are implemented. The format uses the document mode. It's typeset 2D live math input, and we illustrating the techniques of clickable calculus or syntax-free use of calculus. Here are some of the interactive tools that we make use of. You get palettes on the left and embedded components, task templates, tutors, assistants, context panel, so forth. Basic paradigm here is we separate math from Maple. In other words, we don't use Maple to convey math. If math has to be conveyed, we convey it the way it would appear in a textbook. Once the math that we want to implement is clear, then we implement it in Maple. And then there's a pedagogical device here where we resequence concepts and skills. So the idea here is get the concept down first, then worry about picking up the skills later. Okay, let's see how to access the guide. So this is going to be a live demo here. Nothing written down. I'm assuming that users will have access to a copy of Maple that has the guide embedded in it. So here's what you do. Click this question mark, which by which you access the help system. Now you look down here in the help system and you see education, and right under it you see study guides. If you look in education, you will again see study guides. What is in this section is exactly what's in this section. This repetition is by design, because I asked about that. It is intended, that's the way it's going to be. So I am going to open the more accessible study guides. And you see there's more than one study guide. We're talking about the calculus study guide. And you see here there is a table of contents, and there are the chapters, and there's even an appendix. And you can rummage through here, seeing the sections and the examples, or you can bring up this table of contents, which will open in either a new window or a new tab, depending on how you have your Maple set up, and work from there. So let's do that. Let's bring up the table of contents. So from this table of contents, you can make selections. You can see what the sections are. Remember, there are 69 sections. Averages out to about 7 or 8 sections per chapter. So here are the chapters: limits, then differentiation, then applications of differentiation, integration, applications of integration. Then there's that chapter on techniques of integration. After you get some additional techniques of integration, you can do additional applications. There's a section on sequences and series. And then there's an appendix that explains stuff about the use of Maple. So here we had looked at some sections here within the first chapter. Naive limits. You got to get started on limits. I think if you jump in to a precise epsilon delta definition of a limit, that 99.9% of the students sitting in a calculus class who are not going to be math majors are just blown away by this notion of the precise definition of a limit. And I always just save that to the end of the course. But at any rate, naive limits to begin with, limit laws, then you do the trig functions, then limits at infinity and infinite limits. Now you can talk about continuity and the intermediate value theorem. So just to take a look at what one of these sections might be like, let's try limit laws. There are two parts to each of the sections: essentials and examples. Essentials, this is what one would need to have a grasp of to profit from studying the calculus. So the limit laws, some tools in Maple for calculating limits, the limit methods tutor, how you get solution steps, squeeze theorem, limit laws. So here's a statement of the limit laws. This is what you would find in the calculus book, so it's just a reminder to the user that that's what you would have to know. What are the tools? Where are they? How do they work? I'll just illustrate some of this stuff in an example as I go. All right, limit methods tutor. What does it look like? Where do you find it? So essentials and then examples. So in the examples, you would have a hyperlink over to a page where you can see this worked out example. Let's take a quick look at what's in some of these other chapters. Very quick. Differentiation. So what is a derivative? Precise definition, differentiation rules, chain rule, implicit differentiation, derivatives of the various special functions. Then you would go to Applications, tangent normal lines, Newton's method, Taylor polynomials, differentials, and linear approximation, curvature, related rates, then the connection between derivatives and graphs. We have a tool, Maple, that will draw the graph. In the old days, you used derivatives to see what the graph is going to look like. Well, now you can start with what the graph looks like, but you want to know what the connection between derivatives and the shape of the graph might be. Then there's optimization, indeterminate forms, L'Hopital's rule, and the notion of an antiderivative. Chapter 5, we have applications of integration, more straightforward ones, area between curves, volume of the solid revolution, volume by slicing, arc length, area of the surface of revolution. Then we have differential equations, centroids, work, hydrostatic force. In chapter 6, you got the famous work on integration techniques. So parts, which is important. Then you need trig integrals, because when you do trig substitution, you end up with trig integrals. Then you have partial fractions. First there's the algebra, and then there's the integration of the fractions that you get when you do partial fractions, rationalizing substitutions, numeric methods. Chapter 7, you have some more applications of integration. Basically, what you want to do is integrate in polar coordinates. So first you have to have work on polar coordinates. And this is where we have the theorem of Pappus. Chapter 8, sequences and series. The appendix has material on how do you find stuff in Maple, how do you do things in Maple in this point and click functionality. Now let's take a look at some of the examples that I've prepared. I've got them in a little table hyperlinked so I can get right to them. So I'm going to do this epsilon delta definition of a limit first, because it's an example that shows just how different an ebook is from a paper book. So I have this function, and I'm going to use definition, formal definition of a limit, to show that the limit of this expression, x goes to 3, is 3. Now, if you look in typical calculus book right now, you'll find that there are a lot of ad hoc special estimates that are used in order to show that if the function is within so much, in order to get the function within so much of the limit value, you've got to have x within so much of the target value. It doesn't generalize. So this approach is more amenable to a generalization. Clearly, this animation right here is obvious, right? Here you have 3, here you have the graph, you have bounds for x that correspond to an epsilon band. So here's the epsilon band, and you can manipulate it. The important thing to realize here is that this band in x that you see here from the red line to the green line is not symmetric about 3. And that's what makes the estimates so hard. That's why it's so difficult to just solve inequalities, because this band is not symmetric about 3 because of the curvature of the curve. This interval from 3 to the green line is smaller than the interval from the red line to 3, because this is an increasing bit of the function. So Maple is amenable to finding these two endpoints. So basically you are finding a delta L, which is on the left, and a delta R, which is on the right. They're not the same. And then you pick the smaller to make your bound on X. And so that's what I'm doing here. I'm setting the function equal here, 3 minus epsilon, and I'm finding the delta L on the left. And then you do the same thing on the right. You want to make sure that you're picking the smaller one, so there's an effort to discover the smaller one. Here, the smaller one is found analytically. I put delta L over delta R, and if I can show that that ratio is greater than 1, then delta R is the smaller one. You want to use delta R in your estimates, and here I'm showing that the function value compared to 3, absolute value, and in order to sweep the region from 3 minus delta R to 3 plus delta R, I put a multiplier t where the absolute value of t is less than 1. That sweeps that span, a little bit of algebra, and you can show that this distance, or that absolute value there, is less than epsilon, completes the proof. So this is an illustration of what you can do different with an ebook that you do not typically see done with a paper book. Now an example from the differentiation chapter. Differentiation rules. Apply the rules to get the derivative of this function. Define the function, get a stepwise solution. Implement it as if you were working with pencil and paper. So what would be the rules? You would split it up into pluses and the minuses, pull out constant multipliers, use the power rule, do the appropriate algebra. Now Maple will generate this kind of a solution. Use the calculus palette. All right, so let's take a look at the calculus palette. Here's the calculus palette. You have a derivative operator here. You apply the derivative operator to the expression. And here it's echoed back here. You go to the context panel. You'll see Student Calculus 1 if you've loaded the Student Calculus package, and you'll have the option All Solution Steps. So let's do those two steps. Let's load that package. Let's define that function. So having typed that in or copied and pasted it, okay, the context panel has this assign function that makes f this function with that rule. When you come down here, I'll just type that in. We need a derivative operator, so you have the derivative operator, and you apply that to the function f of x. Well, now Maple knows what f of x is. Okay, we want to make this active, so make that executable. Okay, so down here in Student Calculus 1, you have these options, all solution steps. If you click that, you will get this display. It's an annotated list of the solution steps. It describes each of the steps that you have to implement. You can do it interactively. If you go to the spot where we just were, right? You have apply the next step, or what are all of the rules, and you pick the rule you need. Or you can ask for the differentiation methods tutor. Let's take a look down here. Differentiation methods tutor. Where are the tutors? Well, they're up here. Tools, tutors, calculus of a single variable, differentiation methods. Well, that tutor is illustrated here. You're taking this derivative, you have the rules, you pick the rule. If you pick a rule that doesn't make sense, maybe we'll tell you, no, don't do that. You should be thinking about going in this direction, you can get the next step, or you can get all of the steps. So the differentiation tutor is another way of implementing step-by-step computation. Our next example is an application of differentiation. Let's get over to our table here. Tangent lines and normal lines. One of the simpler applications of differentiation. So here is a function. We want to graph it, and on its graph, put the graph of tangent line and normal line. You got to find them. So here is our solution. So mathematical solution, do the math separate from Maple. So you need the value of the derivative. This is the point slope form of a straight line, negative reciprocal of the slope, point slope form of the straight line, and here's the graph that we want to end up with. You can see in red the curve, tangent line in black. I think that's a green normal line. There's a task template for obtaining this tangent line. Now, where are the task templates? Tools, tasks, browse. You get a table of contents, tasks. Okay, this is the path to it. Differential calculus, applications, tangent line. And you insert it by clicking one of these two buttons. Default content means you get this extra verbiage. Minimal content means you get enough to make the thing work. I've got it embedded. So here you put in the function. Where are you drawing this tangent line? Here you click this button, you get the tangent line. You want some of the details. You click this button and you get here the derivative. Here is the value of the derivative at x0, which is 2. This is the y coordinate when x is 2, and here is the point slope form of the straight line, which is the tangent line. So here is your tangent line. Here's a picture, curve plus tangent line. There's a task template similar to this for normal lines. Okay. Fill it out the same way. And then there is a solution from first principles where you implement the steps, but in Maple. So here's the function you assign as a function. Showed you how to do that. F prime at 2 computes to the derivative at 2. So this is the notation you'd see in a textbook. It's computable in Maple. And here's the point slope form of the line. F of 2, that's the function value. Here is the negative reciprocal of the derivative. And here is the construction of the graph. It tells you here how to build that graph. For our next example, we're going to take something from the chapter on integration. In fact, we're going to do an improper integral. So here's the improper integral we want to evaluate. If we were working with a pencil and paper, purely mathematical solution, we would replace the upper limit of infinity with a parameter t. We would let t go to infinity. So the antiderivative of 1 over x squared is minus 1 over x evaluated between the endpoints, and you get this expression. You now take the limit as t goes to infinity. You can see here as t goes to infinity, this piece goes to 0, and the answer is 1. Working in Maple, if you wrote that integral and evaluated it, you would get 1. If you want to do it stepwise and you put the t here, in order to get this integral to evaluate, Maple needs to know something about t. If you would use syntax, you could say assuming t greater than 1, and you would get to t minus 1 over t. To do this integral syntax free, simplify it. So here's the integral. You would go here to simplify, and you would pick something like assuming positive. So that would allow the integral to evaluate. You would get t minus 1 over t. You could then apply the limit operator here, limit. When you click that, you get this pop-up. You have to indicate the limit point is infinity, and you're coming at it from the left, from below. Say OK, and you'd get the limit to be 1. Our next example is again from integration. Area between curves. So region is bounded by some curves. So these are the bounding curves. 1 minus 3x over 2. So we have a line here, something like that. And square root. So a mathematical solution would begin with a picture. So here is a picture. There's your 1, there's the slanty line, and there's the square root. We want the area. We want to integrate over this region with just calculating area. You're going to need to know this point, because in this first integration we're going to do with vertical strips, we're going to integrate dx. And this being an animation shows that as you integrate in dx, when you cross over at point x equals a, or the x coordinate at a, the bounding curves change. Here it's from the green to the black, and here it's from the red to the black, so you need two integrals. Okay. If, on the other hand, you do horizontal strips, integrate horizontally, you're going from this green line to this red line, you really only need one integral, and the integration proceeds as a dy integral. But you would still need the y coordinate at this point, and so it's calculated, and then you can set up the integral as a dy integral. Maple solution requires some of that same information, but how do you get it in Maple? So let's make this curve, the slanty line, we'll call that G. The square root we'll call H. They intersect, so you set G equals H, and you solve that for the x coordinate, and you say A. To get the y coordinate, well, you could, because G is in the form y equals, you could put that AX into G, and you would get the y coordinate. Now, this icon, or this template, comes from, I've got it down in my favorites. It comes from the evaluation template. It's the evaluation command. Okay, so I've made use of that right here. And the integral dx, you need two of them. This is from, what was the color of that line? This is the green line up to 1, and this is the red line up to 1. If you go horizontally, you've got to express y as a, or x as a function of y. So this x as a function of y on here, called g, and the other end, the square root, and that's where you get the y squared. That difference integrated dy gives you this. Simplify gives you that. You float it, you get that. Another application of integration, volume. Well, there's volume revolution and there's volume by slicing. This is an example of volume by slicing, which I think is more difficult to visualize. So we have the volume of a solid whose base in the xy plane is the region bounded by the x-axis, the curves y equals sine x and x equals pi over 2. Cross sections parallel to the YZ plane are equilateral triangles. So of course we can visualize the region and set up the integral without any trouble. I don't think so. This is what the solid looks like. This is an animation that shows, let's just set that in motion. There's an animation that shows the equilateral triangles moving back and forth, filling the volume. Okay, so we need to find the area of one of these equilateral triangles. We thicken it with a dx, a little bit of a dx over here, and then we sum that. Well, you got two ways to find the area of this triangle. You can try to get the height, so you do the manipulations that you require to get the height, or you can use this formula for the area, 1/2 AB sine C, where this would be A and this would be B, and sine of C would be the angle between. So this is a sine X, therefore this is a sine X, and the angle between is 60 degrees, and so the area of this triangle becomes 1/2, that's this 1/2, AB, they're both sine x's, so sine squared x, and the sine of 60 square root of 3 over 2. That's what you have to integrate from 0 to pi over 2. So you write down that integral, evaluate it, and you get this value for the volume of that solid. Now, as a maple solution, you're going to need the area as a function of x. So we'll assume that you have that. If you put it all together, you can see here that you are going to be integrating root 3 over 4 sine squared. So if you write that integral down and evaluate it, you get square root of 3 over 16 pi. If you would to load the Student Calculus 1 package and then ask for all solution steps, and I showed you where that was located, you would get a stepwise solution printed, annotated, printed out. You could also perform the stepwise computations step by step via the context panel, and I showed you before where that was. There is also the tutor methods tutor, so single variable calculus, integration methods. This tutor right here would do the same thing, give you access to the steps, just the way the differentiation methods tutor did. Now for the chapter on the special methods of integration, parts, partial fractions, so forth, I'm going to do this example of the algebra for partial fraction decomposition. All right, so this is just the algebra to get the decomposition. It's a different story where you learn how to evaluate the integrals that result. Those integrals are trig integrals, and they require trig substitution sometimes, and so forth. That's a story for another day. Okay, so here is rational function. Mathematically, here is what you would do with a pencil and paper in order to decompose this fraction. First of all, you need to factor the denominator. It factors nicely. Two linear factors. Because they're two linear factors, the decomposition terms on the right have linear denominators. I like to just multiply through by this denominator on the left. That's typically how I did it. This is what I showed my students. That clears the denominator on the left. And you see that numerator on the left here. So you're going to get cancellation. The x minus 3's cancel, so you get a1 times x minus 4. And over here, you get a2 times x minus 3. And then you collect like powers. So the stuff that multiplies x, a1 plus a2. The stuff that multiplies x to the 0 is minus 4a1 minus 3a2. And now you have to match coefficients. 7 must match a1 plus a2 because this is an identity. And x to the 0 or 1 matches minus 23. Two equations and two unknowns. You have to solve those. So you have some way of solving those two equations. Here is the solution. So now you can write down the decomposition. How would you do that in Maple? What tools does Maple provide? Well, the first thing you can do is simply go to the context panel go down to conversions, and you see convert to partial fractions. Variable is x. So you can get the solution for the decomposition immediately. Now, if you want to see how it is done, then you need to write down the template fractions, and you have to find a1 and a2 for which this becomes an identity. So if you write that equation down and you go to solve, you would see solve as an identity. A pop-up comes up. What is the independent variable? X. What are the two parameters you're looking for? A1 and A2. And now you have the solution. There is a task template. You can find it here. This is the path to it under the heading Algebra, Partial Fractions Stepwise. So how does this thing work? Here you put in the rational function. Then you have to factor the denominator. So this button will factor the denominator. It will do the work for you. But you have to write in the template fractions for the decomposition. After you write them in, you press this button, and it checks whether you have picked the right fractions for the decomposition. If it's correct, keep going. If you get this wrong, there's no sense doing anything else until you get this template right, because otherwise you're just going to go around in circles with meaningless computations. So this path implements the method that I prefer, multiply through by the common denominator, by this denominator here, okay? And the result on the right is expanded out here. Collect like terms, bring everything over so that you have 0 on one side, and you collect like terms. So this is the stuff that multiplies x. This is the stuff that multiplies x to the 0 on a constant term. Each of these expressions has to be 0 because the left-hand side is 0. That's how you get your equations, two equations and two unknowns. You solve those equations. This button will do that for you. You get the 2 and the 5. And now you have the decomposition. Now, can you do that from first principles just using Maple? So here is the rational function. I've called it f. This is the template that you put on the right. I've called that g. And I'm looking at f minus g. So the right-hand side is 0. I don't write the 0 down. And I hit it with a simplify. And Maple makes one fraction. And it has to equal 0. So all of this numerator needs to equal 0. So I just pick off that numerator. I do the collect with respect to x. I pick off the coefficients, and I hit it with a solve, and I get a1 and a2 are 2 and 5. Do a substitute into via the context panel. These are all context panel operations, and I get the decomposition. If you were working with commands, for those who might want to compare to working with commands, here is the function. The command is convert this expression partial fractions, in x. To work with Maple commands and implement the stepwise solution, let's write f equals g. Get the denominator, that's this product, multiply this equation by that, and simplify. You get 7x minus 23 on the left, and this the simplified expression here on the right. Get the coefficients of x and 1, x power 1, and this is x to the power 0. And since this is an equation, you have to map that coefficient command onto both sides of the equation. Those are the two equations you have to solve, so you get it with a solve, and the eval command will take this equation here and evaluate with respect to these two equations, a1 equals 2, a2 equals 5, and you get the decomposition. Or you can say, here is the equation which we want to be an identity in x. So solve identity. Identity is q1 in x, and solve it for a1 and a2, and there's the solution for a1 and a2. A last example, I think we'll do something in polar coordinates, because integration in polar coordinates shows up in this section. So just graphing something in polar coordinates, graph the limison, 1/2 minus cos theta. Well, here's a little widget that might help a student figure out how to graph limison. This slider controls the angle theta, 0 to 360. I think in degrees. I find it easier to think in degrees. Okay, as theta increases from 0 to 360, you can see the radius vector in red, and the curve is being traced here. But what do you notice right at the very beginning? Look at what the radius is. The radius is negative. But this angle is certainly not 36 degrees. It's more than 36. In fact, it's more than 180. So here we have built in that treatment of the negative radius. You add 180 to the angle, and you draw the radius as a positive value. This students find a challenge, and they also find it a challenge to figure out the angles which generate this little interior bubble. So if they had to find an area of the part outside the bubble or the area inside the bubble. They need to know these angles, and this little widget might help them with that task. Now, Maple can draw that with the interactive plot builder. Interactive plot builder brings up a dialog. This is the first dialog it brings up. You select 2D implicit plot because you're bringing it up for this equation. So 2D implicit plot, define what the parameters are going to be. On the next dialog, which you get when you click options, there's a spot where you pick polar with polar axes. So this is interpreted polar, and this is what we mean by polar axes. And I've just defined a grid size to make it look good. Now, if you would simply write the right-hand side, the 1/2 minus cos theta, okay, invoke the plot builder interactively. So here you would go to the context panel and say, pick the plot builder. You bring up the plot builder, select 2D polar plot. You get your 2D polar plot, and automatically the grid is the polar grid. Here you have some commands that will draw this graph. So if you use the plot command, you would just put in the right-hand side. Theta goes from 0 to 2 pi. The coordinates are polar, but the axis coordinates are also polar. That's what generates this set of axes. And I've picked scaling equals constraint so that this looks with the appropriate shape. Now, in the plots package, there is a command polar plot. Give it the right-hand side, R equals the right-hand side. 0 to 2 pi, scaling equals constrained, you would get this picture. If you go plots, because this implicit plot command is in the plots package, give it the equation, and R will go from -1 to 3/2. Theta goes from 0 to 2 pi. Coordinates equals polar. You'll get this graph, but you do not get this axis as you have here. If you apply plot to the right-hand side, theta going from 0 to 2 pi, coordinates equals polar, you would get the graph, but it would not have this background, because to get that background, you have to say axis coordinates equals polar. And as a caution, when you convert a polar expression to Cartesian coordinates, don't do it naively. Be careful. If you replace r with root of x squared plus y squared, and on the right-hand side you replace cos theta with x over the square root, this left-hand side can become negative. But this, I said left-hand side, this right-hand side can become negative. This left-hand side stays positive. You got a problem. You got to be careful. So what you want to do here to keep everything positive is square both sides. Now both sides stay positive. So when you're trying to graph a polar curve and express it in Cartesian coordinates, because maybe you're not having too much luck with the polar form, you got to watch out for these sign changes and deal with them properly. I think we need to stop about here. There are some 460 examples. There's lots more to look at. I don't think we'll have any more time to look at that stuff. Get a copy of Maple. It's up to date. You have access to the study guide. Lots of explorations that you can do. And I'm going to just climb on the soapbox for one little minute here. Notice in this example that we did for partial fractions that the algebra of getting the partial fraction is very, very tedious. If you make a mistake, you end up integrating the wrong stuff. For most students, does it really make sense to drive them through that algebra to get the partial fraction decomposition to just be able to do the integrals? Why not just use Maple and say, okay, Maple, tell me what the partial fraction decomposition is, because I'm only interested in figuring out how to do these integrals. This is the kind of approach that I'm talking about at the beginning, the pedagogical approach that says, get the concept down pat first, before you stress the details of the computation, the computational details. Just personal point of view, just something to remind practitioners in the classroom to think about what they're trying to accomplish. Are they really trying to recreate another 30 or 100 or 300 or 500 mathematicians? Or they're trying to get some students to understand a little bit about what the calculus is and what it can do for them. Okay. Any questions? We'll take care of that now.